Okay, in this little tutorial, we're going to look at the case where we have some power loss. You might recall from before that we had this case of a machine, and we said that you could have some force being applied. We could call that F, say, y1. It moved a small amount dy1, and this allowed us to raise the weight by a small amount dy2, and the weight had a force associated with it, mg. But now we're going to look at the case where there's some lost work or lost energy. So if I'm talking about virtual work, I have force in motion, and I have some power loss that works over some small amount of time, dt. Alternatively, we could do this in terms of power, in which case, instead of thinking about a small motion, I'm thinking about the fact that the lever has some velocity. I'll call it Vy1, and the weight is raised with some velocity. I'll call that Vy2, and now I just talk about a power loss instead of a small amount of virtual work. So in summary, we have input force, power loss times time is force times the small displacement, or if we're working with power, we have force times a velocity minus power loss is force times velocity. So let's take these ideas and use them in the case of a transmission. What I'm going to do is look at the case of a gear where we have two gears meshing, and we have work being done with a force acting upon this second gear. I'll call this second gear gear 2. So what do we have? We have a force that is being transmitted. So there's an input gear, and it's causing this other gear to rotate as well. And the teeth of this gear are bearing upon the teeth of the driven gear. And let's say that we have a tangential force, which is the main force doing the work. I'll call that F sub t. But because the teeth are curved, there's inevitably going to be essentially a side effect force, which is in the radial direction. And this is not a force that's doing work. It's not a useful force, but it's there nonetheless. So on the input side, if we think about power, we have torque, T1, and it's rotating with some angular speed, omega 1. And on the output side, we have torque, tau 2, and it's rotating with the angular speed, omega 2. And the things to observe is that the tangential force, F sub t, this is the one that's transmitting torque into the second gear. And then there's also this radial force, which is doing no work. Okay, so let's look at these two gears in a little more detail and what all the forces are. So here I've redrawn the gears, and we're going to add some dimensions and look a little more carefully at the forces. All right, so as we said, there's the tangential force, F sub t, and at the same point, any point along this tangent line where these teeth are moving, instantaneously they are moving along this tangent line, and they're moving with a velocity, I'll call it v sub t. The input gear is rotating with omega 1, and the output gear is rotating with a velocity omega 2, and we need to add some dimensions. So let's say that this first gear has a pitch radius, I'll call that rp1, and the second gear has a pitch radius, which I'll call rp2. And finally, because these forces, the tangential force and the radial force, let's go ahead and add in the radial force, F sub r. Because there's a tangential force and a radial force on the teeth of this gear, those have to be balanced by equal and opposite reaction forces at the bearing. So let me break that also into two orthogonal components. I'll call them F sub b and F sub f, because this second part is really due to friction. And this is a bit of a preview for what we're going to be doing for the midterm project where we build the Lego crawlers. In the case of the Lego machines, we don't actually have ball bearings or anything fancy. We just have Lego splines which are rotating in holes in Lego bricks. And so the shaft is spinning in a hole, and there's a reasonable amount of friction. It's one of the main sources of power loss. So the point is that there's friction at that bearing, and that is going to be the source of our power loss, and we want to find a way to account for it. So the first thing I want to be able to do is to write some force balances. In this case, one convenient way to do that, I said earlier that the tangential and radial force have to be balanced by forces at the bearing. Now, the tangential and radial forces, those I've split them into two orthogonal components, so they're going to be perpendicular to each other. Meanwhile, the main bearing and the friction bearing force, those also have to be perpendicular to each other. However, they don't actually have to be exactly aligned. What they have to do is to add up to 0, which is why I've shown them drawn in this sort of dotted circle, because you have to be able to do a vector sum and they all add up to 0. And so just to summarize, we have the notes here. The gear tooth forces and the bearing forces have to cancel, so the tangential and radial forces have to equal to the bearing and the friction forces, where the tangential and radial forces are perpendicular to each other, and ditto for the main bearing force and the friction force. Finally, we notice that the friction force, the frictional component of the bearing force, has to be equal to mu times the main normal bearing force. And to understand this a little better, it's worthwhile kind of zooming in more detail. So at this point, let me erase some of the markup, and let's do a zoomed in view of what exactly is going on with this shaft. Once again, recall, we have the tangential force and velocity. We have the main bearing force, which I've been calling F sub B. And then it's really not exactly a point contact. It's kind of distributed along this side of the bearing. And that is what is giving rise to a frictional force, which I'll call F sub F. Well, for power, remember, so we have F sub F is equal to mu, the coefficient of friction, times F sub B. And it's going to have a sliding velocity. And what is that? That's because this bearing is spinning like so with omega 2. And what it's actually doing is sliding in a slightly larger hole. So if it's sliding like this, then the friction force is directed that way, and the velocity is just going to be equal to the radius of this shaft. I'll call that r of the shaft, r sub s, times omega 2. So that is going to be equal to r sub s times omega 2. So finally, the power for this setup can be written like this. The input power is the tangential force with its velocity moving along. That's the part that's doing work. And in this case, by the way, what is that tangential velocity? Well, it's just the rotational speed of the gear times the radius of that gear out to the pitch center, which recall was r sub p, rp2. Oh, I drew it there already. And what's getting lost is due to friction, which is at this shaft here. It's the friction force times the sliding velocity, omega 2 r sub s, where that frictional force is the coefficient of friction times the main bearing force. And then finally, the output power, what gets transmitted by this gear to its shaft, is omega 2 and the torque associated with that. So to summarize, we have some input power, which is a tangential force times the velocity of the gears along that tangent plane, which you can also write in terms of the angular speed of that gear and its pitch radius. Some power is getting lost due to friction at the bearing. this power loss, it's proportional to the bearing forces and the speed. And the force is proportional to the gear tooth forces. It's a constant percentage of them. And this is why it works to say that power loss for something like a transmission is a constant percentage of the input power. For example, 5% or something like that. One more thing. Note that the output velocity, omega 2, it has to be exactly equal to the ratio of the gear sizes, RP1 over RP2 times omega 1. That's because the teeth aren't slipping. But we recall from before, when we had cases with no loss, that you could write that the output torque would be exactly equal to the radius of the second gear divided by the radius of the first gear times the input torque. That's not true anymore, because if it were, you'd have no loss. So it's got to be something less than that. And in fact, what you can write finally is the total equation with power loss. So we have our output power, P out, and that has to be equal to the input power, P in, minus our power loss, which is a function of friction, the bearing forces, and the speed of the gear and its shaft radius. And if you actually knew all those things, you knew the diameter of the shaft and the coefficient of friction and so on, you could calculate this. But what people are more likely to do is to say for a transmission, we've measured that there's something like 5% of P in, and then if I increase the torque or increase the speed, that percentage remains constant.